Okay, welcome to another session of EL 164. Today we're going to continue to talk about the basics of PLC programming, Chapter 5. Basics of PLC programming. So here we are. We're looking at some of the real rudimentary stuff. This class is primarily focused on the Allen Bradley solution. So we're going to be dealing a lot with their terminology and their formats. So Allen Bradley is one of the leading manufacturers of a PLC. There's others out there, GE, Siemens, and Automation Direct. All are valid PLCs, and I think actually last unit we had an opportunity to go online and look at some of those in our lab, and hopefully you guys managed to get through all of that. First thing I want to make you aware of is the examinative close, examinative open. That's XIC, XIO. As you notice here, you'll see what looks to be two parallel lines and then two parallel lines with a slash through it. Essentially what they're saying here is that when the input goes high, this contact will be illustrated as or when it turns to a true or one state, this contact will close, and the logic on the right hand side of this will go active. Kind of like a contact in a relay. If you're familiar with relays, contacts and relays will open and close. As they close, it allows power to flow through the contacts to the device that you're trying to control. Same principle applies here, is whether it's be a push button or a contact from relay. So what they've got here is examine if open, which essentially is what they call in the industry a normally closed contact, meaning that when it is off, it is supplying power to the right-hand side of it. When you turn it on, it opens the circuit and turns off power to the right side of it. So that's the real rudimentary basics of the PLC. So first thing we step into is 5.1 processor memory organization. So when we're dealing with PLCs, there's two different styles, as we learned in the last unit. There's the fixed CPU and then the modular CPU. In this particular illustration, we're looking at a modular CPU or PLC. Typically, you'll have the power supply to the left, the CPU or the brains of the operation, and then a series of input and output cards required for each application. So depending on the application, it will depend on the number of cards you have. So one of the points that they bring us right into is the software that controls the PLC. This is the interface software. This software is the only way to get the information to and from the PLC. The only thing that the PLC really understands as an interface to an operator, such as what we're going to be when it comes to developing programs. So this is how we get that information to the PLC. This is how the PLC goes back and tells us if there's a problem or if we've got issues. We got to set up a configuration. We got to set up the look at how to develop a program and all those things. But this is the software that we're going to be doing all of that in. So here we have kind of divided into two separate files. We got the program files and data files. So this is getting, we're diving right into it here. So you'll see here we got output files, input files, status file, bit. So you will see all these timers, counters, controls, integer, floating point, all these different associations to a data file. And then you got program files on here. You got the system file, 0, 1, 2, and then program file. So here they're talking about is this is where 2 is where we're going to be having our main program is going to reside inside the PLC. And then any subroutines or other routines, we'll be getting into that in the future here. But when we add multiple sub programs, we'll be using subroutines. So program files. So here we are looking at some program files. Here we got our first real view of ladder logic. So what we're looking at here is a series of contacts, normally opens and normally close. As each one of these close or as this address in an input card turns on, you will see this highlight in the program. And then when all 3 of these components are highlighted, this piece here will highlight on the right. And the same thing goes for this guy here at the bottom. So when this highlights. And the normally closed means what? The input's got to be off. And for normally open, the input's got to be on. They're kind of going in here and so on, showing us program files and system 0, system 1, and ladder 2. They're just showing us where those files reside under the user program. And here is where the data files are. So the data file, this is a common point that I think a lot of people miss, and I want to make sure you guys are real clear on, is a PLC is a series of data tables. That's all it really is. That's all it knows. It knows the information in these data tables, okay? When we think PLCs, quite often we think ladder logic and contacts and coils and blah, 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 all that stuff going on, and timers and counters and all that stuff. But the reality is the PLC does nothing more than review what's going on in these data tables. It's looking for 1s and 0s in these data tables, and it's looking for values in these counters and timers and all that sort of thing. So, so any information in one word can be viewed and manipulated to work in other words. So what I'm getting at is that any information, any PLC, you can utilize in your program to develop solutions to problems and while programming a machine. So here are the data files. Now this is the 500 series software, so it does address a little bit different than the 5000, and we'll be getting into that. And I think the book does does kind of flip back and forth a little bit on some of that information, but essentially it's telling us that there's a data file for outputs, inputs, status, binary, timers, counters, control, integer, and float. So so there's a total of 9 separate files for that information. So we talked about this a little bit in the last section, so we're going to continue with this a little further, keep building on it. So when we're looking at an I, for instance, we're looking at the I as an input. Looking at an O, we're looking at an O as an output. So that defines whether this slot in this PLC is reading an input or writing an output. The next piece of this is this slot number that I got indicated here. Now the colon is a separator, so it's just keeping the input-output separated from the rest. Okay, so the next piece is the slot number. Slot number, as you can note here, is a 1. Well, they got in1, so in1's got to be here in slot 1. Let me step back one step here. I forgot to mention, the CPU always resides in slot 0. So then that leaves slot 1, 2, and 3 for inputs and outputs. So, so what we're looking at here is slot 1, as you can see here, I1, and then they've got a 2 in there. So I'm looking at slot 1, input 2, and it's an input card. Here, if I was looking at the output card, I'm looking at output, slot 2, output 2, so I'm looking at this slot here, bit 11. So I come in down here and looking at bit 11. So that's the bit number that we're looking for. Okay, so here he's adding a normally open contact, or an XIC, putting in an address, putting in a coil. This would be an output address. So that is how you develop code. That's just nothing more than when this input turns on here, closes this contact, and turns on this output. So here we are looking at data tables again. So again, input 0 through 4 is shown here, and output 0 through 4. So it's 4 different input and output cards. And then they're showing us the addressing here is associated with those. 0 through 15 for each one of those words. As you can note here, it's reading it in binary. The radix is in binary, or the base of 2. The table is reading input I1, and this table here is reading O0. So as we're making and breaking these contacts, or opening and closing these contacts, so as you can see here, we have this contact here. When it's in open, it's in an off state. That associated bit to that location, 0, 1, 2, of whatever word this or slot this card is in. Associated slot word number is going to be the address location. So they didn't provide that here. We're just looking at bit level here. So here we're just looking at bit 0, 1, 2. 0, 1, 2 is off. Okay. The next location we're looking at here is 0, 1, 2, 3, 4, 5, 6. Bit number 6. So if I'm looking at bit number 6 as being on, I can go over here 0, 1, 2, 3, 4, 5, 6. And that shows us that location being on. So here we're seeing that input actually turn on and off. Output image table, same principle. Okay, so the only difference is instead of a card writing to the PLC is writing to a card. So we're writing, the PLC writes this data table, and this data table updates the information to the output card. So what we're looking at here is 0, 1, 2, 3, 4. So we'll be looking at bit 4 on this guy. So if we go 0, oh, I don't know what they got going on here. Why did they do that? 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3. I'm not sure what this display is actually trying to define here, but anyways, they're showing us if I'm in this location, if there's a 0 here, this is going to be off. If there's a 1 here, this is going to be on. Let's see, the next slide. Okay, here we are. So they're showing us how both those guys will turn on and off. So as you can see here, this is a fixed number of inputs now. This doesn't have a modular, so how is it addressed? Look at here, they just did a little different here. So they just said there isn't a slot 1, 2, 3, 4. They just go I0 through I19 because there is no slots associated to it. It doesn't need the addressing of a I:1 blah blah blah. It just has input 0 through input 19. That's kind of nice. And then for the outputs, we got this very similar thing. We got output 0 through output 11 here, giving us 12 outputs. Excuse me. So, and also a couple points I want to share is I'm noting the commons. Here we got a couple of commons here. And notice all the separate commons we have for the outputs. One of the reasons that the manufacturers provide many commons for a PLC output is so we can isolate the control of those outputs. The PLC can never be used as a safety device, so we have to, in order to create a safe environment for our operators and fellow employees, what we have to do is we have to control the signals going to those outputs using safety devices like safety relays, safety circuits, gate circuits, these kind of things. So when the operator's in a zone or an area that motion does take place in, that there is no motion. Everything ceases to move, and with that gate, with this power disabled here, none of these outputs can turn on. Program scan. Okay, so here we are. We're talking program scan. What does that mean for us? This is how the PLC actually operates. That means that when the PLC goes out and runs a program, these are the steps that it's going through to make that happen. Excuse me. First thing we do is we scan the inputs. We're going out there, we're looking at the inputs, seeing what's going on. Is there any change in state in the inputs or whatnot? Then it goes through and it runs the program. It says, based on the information from the new inputs, turn on the PLC, let's run the PLC program, which is going to turn on bits on and off and all sorts of fun stuff. And then, based on the information that the program scan came up with, we're going to have output scan take place. So what's going to take place there is going to basically update the outputs. That means it'll be turning on lights and solenoids and valves and all sorts of fun stuff there. And then the last piece of this is they got housekeeping. This one isn't always included. Sometimes you'll just see, if someone asks what's the scan process of a PLC, quite often people go input, scan the inputs, run the program, and update the outputs. Sometimes they skip this housekeeping piece, which I'm give or take on it. I'm flexible with it, but the idea is that here you're going to see this is where it does diagnostics, this is where it does the communications, this is where it does all those extras that a PLC does take place. Also, at the same time, I need you to be aware that in the latest version, the 5000 version of the PLC, they do what they call an asynchronous scan, which what that means is that they do all this at the same time. So now they're not going through the process of scanning an input and updating the program and updating the outputs and all that. It just does it all at the same time. It's constantly reading the inputs in, it's constantly running the program, and it's constantly updating the outputs, all at the same time. What that does is just, it improves the process itself. So there isn't any delay waiting for this process to complete, this process to complete, this process to complete, before it gets back to this process again. So there's no delay there. It's all taking place at the same time. So let's move on here. So the time it takes to complete a scan cycle is measured, okay, so basically what they're stating here is how long does it take for the processor to go from reading the inputs, run the program, update the outputs, do the housekeeping, and then go back to reading the inputs again. And this is a set amount of time. Now, even the newer processors, the 5000 series software, even though it is asynchronous, there still is a scan time. It still takes time to go out and do all that information and then come back and complete that process. But what we'll find is in like the 500 version, we will find a scan time of somewhere in the range of, say, 8 to 10 milliseconds. In the new processor, the 5000, we're going to find a scan time more along the lines of 4 to 5 milliseconds, 4 to 5 nanoseconds. We get into the nanoseconds. We get really fast. So it's a big difference. So it's not. It's a lot more advanced technology. So it is able to move way faster. Let's see if we can move along here. So again, the speed of the processor, the length of the ladder program, and the type of instructions executed all have an impact on that scan rate. So if you can imagine, if you have 10 I/O points versus 10,000 I/O points, you got to believe that the scan rate is going to be way slower than at the 10,000 it will be at the 10. It just makes sense. The more work you got to do, the longer it's going to take you to do it. So that's something to be aware of. So again, in the hardware circuit, there must be continuity for a load to energize. It's the same thing for the PLC program. Let's take a look and see what that has to say for us. As I mentioned before, when that continuity takes place, when we get this highlight point here, that means I've got a continuity through this open contact. This guy here will highlight. So as you can see, the little bars here, that's indicating that this is active and this is active. And this contact, this input to that PLC is on, highlighting this, turning on this. If this input here is off, as you can see here, there is no highlighting here and no contact is here. So again, overview of the data flow during the process scan. So scan examines the information, and then the PLC runs the program and updates the outputs. So it extracts, it writes to this data table. This program writes to an address in the data table. That data table outputs to the output modules. So here it is in a full picture here. So if you can see here, we've got an input. So this would be slot 3, bit 6, or terminal 6 on this input module. And this would be slot 4, terminal 7 over here. So when we make this switch here, this I36 will come on. It'll turn on this out 4-7 right to this data table. That data table writes the information to that card, and that corresponding output turns on. And if you can imagine, you have a series of inputs, so you have multiple inputs and multiple outputs. Noting here that all the inputs are to the left and the outputs are to the right. This is the way all PLC programs are working. The program scan itself, the way the program works, it always reads down and to the right. Down and to the right. So keep that in mind. So when a program is being scanned, it's coming down and to the right. So it comes in here. The program starts at the top, comes down, starts reading to the right. Is this contact closed? Yes or no? comes down here. If this contact was closed, then it turns this guy on, comes down here, falls to the next screen, falls to the next line. Is this contact closed? Is this contact closed? No. Don't turn this guy on. Going down here, fall back to here. Is this guy on or is this guy on? Don't turn this guy on. So that's pretty much how it works. All the way to the bottom of the program, and then as you can see here, when it gets to the bottom of the program, it starts at the top again and does it all over again. PLC programming languages. So structured text is a solution that's out there. My last few years of working in industry, I saw a lot of young controls engineers using structured text. They get pretty fast and efficient with installing that sort of thing. So I do believe you're going to start seeing more and more of that in industry. I started out using ladder diagram. It seems to be it's a graphical type of a solution that's easy to follow. You don't have to be a expert programmer to really understand and follow how it works. That's the idea behind it. I do know that it does get very complicated easily because there's so many little tricks and whatnot you have to be aware of when developing code using ladder that it can be difficult to validate all of that. But they do have something called block diagram and sequential flow chart, function chart. Those you don't see those so much. There's a few applications I ran into that into safety relays once, safety PLCs, excuse me, and that's about the only place I've run into that. So, okay, this is a common issue I run into, and this is something I want you guys all to really pay close attention to. When you're asked to develop a circuit, a hardwire relay controlled circuit, it should look something like this. You notice the terminals, there's actually a schematic of a limit switch, a schematic of a push button. Some contacts are normally open and normally closed, and a solenoid. Notice how that differs from the ladder diagram. It's just contacts, no terminals, no devices, and real basic terminology here. So just keep that in mind, because I do have it from time to time where students get the two confused. I asked for a ladder diagram, and I actually received a hardwired control circuit, and or vice versa. And so when I'm asking for a schematic from the class, make sure you understand the difference there. So here we're looking at, again, a further description of what a hardware relay control circuit would look like. So here we got a push button, a relay contact, normally closed relay contact, a solenoid, and a limit switch. One of the points that they're bringing here is the understanding of ands and ors. I don't know if all of you have digital at this point or not. If there's when you're looking at ands and or statements, you're looking at when A and B have to be on in order for the output to turn on. That's essentially what we're looking at. So in an or statement where A or B has to be on in order for the device to be on. And here we have A and not B have to be on in order to turn on the output. So it's really that basic. It's nothing more complicated than that. So that's what we're looking at there. So here's some of that function diagram stuff I was telling you about. Typically you don't see a truckload of this out there, a little bit maybe, but essentially what you're looking at is ladder logic at the top and then a functional block at the bottom. Same principles apply though. It's got N1, N2, ANDed together for an output. Sensor 1 and sensor 2 have to be ANDed in order to turn the output. Same principle applies. Sequential function chart, again, this is not something that I worked with much, so I'm going to just kind of just bring it here. This is not something you're going to see a whole lot of. I've been doing the business for a long time, and that's not something you see a ton of. So, structured text, yes, this is something you will be running into. I guarantee it. I have no doubt at some point you will be seeing something like this. And this circuit here at the top is exactly the same as this down here in the bottom, if you can believe it. So if you look at this, you see sensor 1 and sensor 2 have to be on turn the output. So you got sensor 1 and sensor 2. Then solenoid 1 equals 1. Else if, so this is like an or kind of thing, or if sensors 3 and 4 and not 5, then turn on solenoid 1. So it's the same thing, just in word format essentially. So just keep that in mind. Try not to let this scare you off too much. You really just, if you read it closely, you can kind of get the same gist as this. Bit level logic. So here the ladder diagram language is a symbolic set of instructions used to create the controller program. So here we are, we're looking at a series of contacts and coils. So the symbols are arranged to obtain the desired control logic. So again, you can arrange these any way you want, normally opens, normally closed, and contact coils and whatnot. The examine if closed instruction is a normally open, they call it a normally open contact, something that looks like this, and it's closed when it's made. So when you turn on this input, you close this guy. So you push down on this guy, and that makes it out. So that makes it a examine if closed. The memory bit is set to 1 or 0 depending on the status of the input. So if it's normally closed, it'd be setting to 0. If it's normally open, it'll be set to 1. So that's what they're stating here. So we have this guy here. We close the contact. We make that input turn on. We release that push button. It sets it to a 0. And in the program, that would show as not highlighted. As you can see here, when he closes that contact, it turns on this output as well. We got 1, 4 turning on and turning on that output. The examine if open contact is a normally closed contact, as you can see here with a line through it. So examine it open. So when you think of these examine if closed, examine if open, think about the status that you're looking at. So in the event that this guy is active, this input is on, this is going to be off. So examine if open, that's what they're saying. In the other one where it was examine if closed, this is going to turn on or highlight when the contact is on, allowing it power to flow. So here we got with the push button closed, there is a 1 there, but this guy is now open, so it is not highlighted. And then we press release the button. So this is a 0, and now we've highlighted this, indicating that there is flow through this instruction. And we'll illustrate that here. So now, as you can see, before he pushes the button, we've got flow to the output. When he releases the push button, or when he pushes the button, it turns it off. And when he releases it, it turns it on. So like we talked about at the beginning, examine if closed, examine if open. So bit status is false, bit status is true when it's on, when the push button is pressed. And this guy is, the bit status is opposite of the other one. OTE. OTE is output energize input. Okay, so OUT energize. Think of it that way, okay? When you see OTE, that is the output energize. So that means that's the device. This is the command that's going to turn on the output in the PLC. So we need to get all the signals in front of this guy turned on, so this guy will turn on. So that's the goal. So as you can see here, we've got output 2, 1. I've got this contact in, this output's turning on. It's writing to this data table that information from this location, dumping it right in the data table, and then this card is getting updated with that information, turning on the corresponding output. And then here they're also illustrating the inputs. So we got 1, 1 and 1, 4 turning on down here. So when 1, 1 and 1, 4 are both on, output 2, 1 turns on. So here again, we're kind of going through this a little further. As that contact is open, this bit status is off. When this contact is closed, the bit status is on. Here they use the same address, but they use it normally open and they use it normally closed. So you can see two separate outputs turn on with the action of pressing one button, right? So you got the 1, 0 when it turns on this output. When you release it, it turns on this output. That's a pretty good example. So here we are, we're looking at some more ladder programs. So we're looking at outputs and their relation to what the inputs are doing. So here, these series of inputs either have to be on and or off to operate correctly, to get this output to turn on. One of the circuits that I want to make you aware that we will be experiencing a lot of time with, this is called the seal-in circuit. This is our first exposure to one. What you'll see is this contact here has the same address as this. They call it a seal-in or a start-stop circuit. It's a very, very common circuit in the PLC world. So what you have to do is you have to make these two contacts. This has got to come on. This has to actually be off to close that normally closed contact. And this output will turn on, which will turn this guy on, and the continuity for that output will stay on, even if you remove these two switches. So if you were to turn this one off and this one on, it would still be on. It would stay on until what? We hit I3. At that point, when we pressed I3, it would turn off. Very common circuit. So here we're looking at some left to right true logical path. So here if we have false, true, true, false, we're going to be off. Okay, so if we're true here, we're going to be true here. If we're false here but true here, and true, true here, will be true and true there. So. And an illustration of that. Noting how they press separate inputs and turn on separate outputs. Notice how when these lights are lit up, we got the they're showing the lights here as well, so indicating that actually lights are turning on in the real world. Instruction addressing. So we're going to get into a little bit of the addressing now. Start talking about that. Again, I want you to be aware that the 5000 address is a little bit different, but the principles still apply. So that's why we learned this as well. So if you do run into some of this older hardware, you still get an understanding of how it addresses. But you also have indicator on how the new stuff will work as well. So they'll be going through that here in a little bit. So looking at this. The first component they've got there is the output image table here. They picked output 4/6, so it's got to be slot 4, bit 6. So we'll count over here 0, 1, 2, 3, 4, 5, 6, bit 6. So that is correct. So we've got output 4/6, and that is where they tie the output to. So when the data table is on, the output should turn on. On the input side of things, we've got input 312. So if we come over here, count to 312, we got there. That's coming on. And if we count from the right to the left, so we count over 12, we should see that guy on as well, as we'll see here. All right, 312, output 4/6, and those two are active, and the light would be on at that point. So now they're going to show us some addressing techniques. Well, I guess we're going to just drag them from there. This doesn't really work in PLC. This works in simulation. Okay, so they're bringing up the image table for the input, and they'll bring out the output table as well. So now we're looking at both the input and output table. So here we are. We're actually looking at some addresses at this point in the 5000 realm. So this is, as you can see here, local 1, idata.0.1.2. These are used in the 5000 controllers. So as you can see here, the Logix 5000 controllers. So a little more detailed, a little more information there, but telling you basically where that information is located. Again, same idea though. Gives you rack, slot, bit locations. So local 1, idata means input data, 0, 1, so bit 0, bit 1, bit 2, bit 3, as right on down the line, and then you've got local 2, out data, so that's output data dot 0, so it's bit 0 of output data. So how that all works. I/O connection diagram. So again, I'm not trying to be a dead horse here, but just trying to give you an idea. So when that input is assigned to a bit or a address, it's a terminal on an input or an output card. It's a terminal. It's not, and that same terminal is associated to an address inside the PLC. So those have to correspond in order to get the information from this location to the correct address inside the PLC. Branch instructions. Okay, so a branch instruction. This is something that Allen Bradley and all the PLCs have. It's branch instructions, of course, but the Allen Bradley representation of the branch looks something of this nature. You click on this button and it allows you to create a branch. And we'll be getting into some of that in lab this week, so discussing that. Here's the branch here. You click on that, provides you that little loop there. So now you can come here, put a contact, as well as place one underneath it as well. There you go. Just like that. And that's how that works. Parallel branches, again, can be used a lot more in combinations. So you got A and not B, or C to turn on D. So here's it rolling around it. And here's some different applications again. Something that you will see in industry is they'll stack outputs, something very similar to this, on top of each other. That allows you to control multiple outputs with just a couple of inputs here. And we're getting even into more complicated stuff here, where you got multiple branches in what they call a nested loop, which is this branch is nested in this branch and nested in this branch kind of thing. A branch within a branch kind of thing. So. And here they're giving you some kind of limitations. I'm thinking they blew these limitations out a long time ago, because I've seen some programs that were 8 and 10 pages long as far as lines down and lines left and right. So I don't believe maximum is 10 contacts anymore, but you'll experience some of those opportunities on your own, I hope. Not really going to get too much into this. This is that Boolean equation. Some of you guys that have taken digital already probably experienced some of this stuff. I'm going to leave the Boolean to the digital guys, because we don't really talk too much Boolean. We do a lot of binary stuff, but we're talking contacts and inputs and outputs. We don't usually get too much into the Boolean aspects of things. So I'm going to kind of blow through that. Internal relays, essentially what they're saying here is that we quite often develop our PLC programs using what we call internal bits. That way we're not turning on outputs and flashing lights and all these different things. When we're developing our code, we want to develop everything using internals. And then once we got our logic all developed, then we go back and we turn on the outputs based on those internals. So we use the internals as our logic, and then once we've developed all our code, then we go back and we turn on contacts from this internal relays to turn on outputs, and we'll be getting further into that in the future here. Here they're just referring to the B3 as the binary or the internal bit for the 500 series software. So it's a very common bit for the 500, used for many, many different applications. The 5000, you can create your own addressing. So we're not limited to using something called B3. We can call it our binary bits or whatever we want to call it. So here they're just kind of going into more and more detail on that. So we're noticing here the address of this B3 is an internal relay, and it turns on a coil just as if it was a real world output, but it doesn't actually turn anything on in the output or in an output card. It just keeps it internal to the PLC, turning on inputs or turning on bits inside the data table that allow you to create logic such as this. So here they've got a series of inputs all tied together, turning on an internal bit, so that B313 turns on, and then they continue turning on more inputs, and then eventually that second, that 20 will turn on. Okay, programming examine if closed and examine if open instructions. So again, normally open, normally closed. I hope I know this is a lot of review here, so we're kind of been through this. So I'm going to kind of zip through some of this a little faster. So again, they're showing us here PB1 is normally open, PB2 is normally closed. So here you would show the same thing in a PLC with normally open, and PB2 would be in a normally closed state here. So notice how PB2 is on unless you press the button. Examine if open instruction. Here we are. We're looking at a push button again, or a relay. This push button closes. This turns this relay on, turns the light off, so it operates opposite of what you'd think. So let's take a look at what the simulation does here. So when you press the button, what the output turns off. Examine if closed and examine if open. So here they're just doing some time aspects to it. So I'm going to kind of zip through some of this. I don't know, ladder diagrams. So here we are. We're looking at the RSLogix. We've got the 500 and we got the 5000. We're going to be working mostly in the 5000 this semester. Just using the 500 for learning some new concepts and whatnot, but mostly we'll be working in the 5000 in lab, and hopefully sooner than later we'll get you guys back in on campus and get some real hands-on with this stuff. I'm hoping that for 166, if nothing else, we'll be able to teach you guys some hands-on with the 5000. So here is a video or a picture of the 500 again. So this is the software. It looks very similar to the 5000. Really very difficult to distinguish the two from each other. Just they operate just pretty much the same way. So here's the toolbar. This is where we find those normally open, examine if closed, examine if open, and OTE commands. When we get into the lab, we'll be actually getting into some of this hardware configuration, and there'll be an opportunity to actually see some of this in place. So this is kind of the nuts and bolts of the processor. You gotta set up that processor so the program that you're communicating to the CPU with is reading the same. It has the same information that the PLC has. So, for instance, you got to make sure you select the right CPU, the right number of inputs, the right number of outputs, the right cards that are in that slots, in those slots, and it's pretty. It can be time consuming, but it's not so bad. We'll get through all that in lab. Some more I/O configuration screens. Again, noticing here that you got to pick the rack, you got to pick the I/O cards, and then notice the CPUs are already selected. You got to select that when you open up the program. So there's a few steps here. We'll be going through all those. Okay, so here's the data table for the B3s. Some ladder logic again. I'm going to kind of zip through some of these, so because we're starting to get to about the hour mark, and I don't want to go much. Mode of operation. We have run, remote run, and program mode. These are the three basic modes for all PLCs. When you are in run mode, the only thing that PLC will do is run the program. So you can't get in there and tweak it and modify it and all these things. You're completely locked out from making modifications. Your PLC will do nothing but more than run the program. In remote mode, what that means is it allows you as a programmer to switch it from run mode to program mode remotely, and you can edit, you can tweak it, you can modify the program as needed online in any remote location, and the processor will allow you to do all of that. And in program mode is the one mode where the PLC will not run. All it will allow you to do is download and upload and modify the program. It will not test it. You got to switch it back to either remote run or run mode. It's been my experience, most processors are always left in remote run mode. That gives you the most flexibility and the ability to get in there and edit the program while the process is running, so you can monitor it, you can edit it, and get things back online when need be. So here's some program mode kind of reiterates what I just stated here. Test mode, they do have what they call a test mode as well. That allows you to make online edits. Typically in 164 we don't do any online editing. We save that for 166. Connecting with analog devices, just going to make you aware, analog signals are out there. They don't consist of on or off. They're variance between 0 and 10, or 0 or minus 10 and plus 10, just some range of values, so it's not an on and off state. And we do have input and output cards that do read that range. Those are analog inputs and analog output cards, by the way. So what they're stating here is, as an analog signal comes into the card, then you got an ADC, which is the analog to digital converter, and it switches that analog signal to a DC, or a binary output. So what it basically is doing is taking some numeric value, like we did when we did our own earlier, when we did a decimal to binary conversion. That's really what this ADC is doing. It's doing some value, some analog signal, say it's getting some value, say 256 or 300 or 500, and it's converting that into a series of ones and zeros that the PLC can understand. That's really all it does. So this is an analog reading. It's reading the tank level, and then telling the PLC what that tank level is, and then opening and closing a valve to control how that water level is maintained. So that's the analog version of that, or how that's controlled. So this is the end of chapter 5. I'll be putting together a lab associated with this as well, so you will get somewhat of a hands-on feel of that. Unfortunately, we won't be meeting in the lab to do the hands-on. It'll be a video, unfortunately. But anyways, you guys have a wonderful day, and we will catch up with you later.